At this point, we've studied the first law of thermodynamics, and we know that for a process to occur, it must satisfy the first law. This condition, however, is not sufficient for processes to occur. Let's consider an open container with some fluid at room temperature. The fluid is exposed to the atmosphere, and we're going to look at two different cases. For the first, the container is placed on a surface that is many times hotter than atmospheric conditions. The fluid absorbs heat from the surface, and after some time, it is removed from the surface and cools off until it returns to its initial state, transferring all of that heat to its surroundings. The fluid has gone through a cycle and is now back to its initial state. Here, the first law of thermodynamics is satisfied because energy is conserved and the net heat absorbed by the fluid is equal to the net work done by it, which is equal to 0. For the second case, the fluid starts absorbing heat from the atmosphere and continues doing so even after it is considerably hotter than the atmosphere. The container is then placed on the surface, which is at a higher temperature than the fluid, and all the heat the fluid absorbed is transferred to the surface. In this case, the first law is also satisfied. But we know that this second scenario is simply impossible because heat only flows from a body at a relatively higher temperature to one at a lower temperature. So, although the first law is satisfied, this process still cannot happen. This tells us that obeying the first law of thermodynamics is necessary, but is not sufficient for a process to occur. The second law of thermodynamics gives us a basis for assessing whether or not a process can occur based on the direction of energy flow. Before we state the second law of thermodynamics or discuss it further, we have to talk about heat engines, refrigerators, and heat pumps. All of these devices operate in a cycle and usually involve a fluid which heat is transferred to and from while undergoing a cycle. This fluid is called the working fluid. Heat engines are devices used to convert heat energy to work. They receive heat from a high temperature source, convert part of this heat to work, and reject the remaining heat to a low temperature body or sink. QH is the heat received from the source, and QL is the heat transferred to the sink. From the first law of thermodynamics, the net heat transferred to our system or our heat engine is equal to the net work done by it. So QH minus QL is equal to W, the net work done by the heat engine. For a heat engine, not all of the heat supplied will be converted to work. Some of it will be given up to the sink as waste heat. For any heat engine, QL cannot be 0. So the efficiency of any heat engine will be a measure of how much of the heat it can convert to useful work, and we call this the thermal efficiency of a heat engine. So the thermal efficiency is equal to the net work output divided by the total work input, which is W divided by QH. From the first law, we know that W equals QH minus QL. So the thermal efficiency of a heat engine is given as QH minus QL divided by QH, or 1 minus QL divided by QH. Now let's solve a problem that involves a heat engine. Heat is transferred to a heat engine from a furnace at the rate of 80 megawatts. If the rate of waste heat rejection to a nearby river is 50 megawatts, determine the net power output and the thermal efficiency for this heat engine. So the rate at which heat is transferred from the high temperature source, .QH, equals 80 megawatts, and the rate at which heat is rejected to the low temperature sink, .QL, is equal to 50 megawatts. From the first law, if QH minus QL equals W, the work done by the heat engine, then .QH minus .QL will be equal to .W, the rate at which work is done by the heat engine. So using this, we obtain the rate at which work is done by this heat engine as 30 megawatts. So for the thermal efficiency, if the thermal efficiency equals W, the work done by the heat engine, divided by QH, the heat supplied to the heat engine, we can also write the thermal efficiency as .W divided by .QH. And using this, we obtain the thermal efficiency of our heat engine as 0.375. This tells us that the heat engine converts only 37.5% of the heat it receives into work. A refrigerator is a device which transfers heat from a low temperature medium to a high temperature medium. In a refrigerator, the working fluid is called a refrigerant. And for a refrigerator to function, it must receive work input. For a refrigerator, QL is the amount of heat absorbed from the low temperature or refrigerated environment, and QH is the heat given off to the relatively warmer region, which could be the atmosphere in some cases. So from the first law, the net heat supplied to the refrigerator is equal to the net work output of the refrigerator. So QL minus QH equals minus W, because for a refrigerator, we have work input instead of work output. So QH minus QL equals W. For an amount of heat, QL, to be removed from a space, an amount of work input, W, is required. The coefficient of performance for a refrigerator can be expressed as the desired output divided by the required work input. And this gives us QL divided by W. So we can express the coefficient of performance of a refrigerator as QL divided by QH minus QL, or the inverse of QH divided by QL minus 1. A heat pump is basically a refrigerator. The only difference is, for a heat pump, the focus is the heated space. So a refrigerator is used for cooling a space by removing heat from the space and supplying it to a warmer region, while a heat pump, on the other hand, is used for heating by removing heat from a cooler space and supplying this heat to our desired space. For a heat pump, the desired output is the heat supplied to the relatively higher region, QH. So its coefficient of performance will be QH divided by W, or QH divided by QH minus QL. We can also write this as the inverse of 1 minus QL divided by QH. So let's solve a couple of examples on refrigerators and heat pumps. The first example. The food compartment of a refrigerator is maintained at 4 degrees Celsius by removing heat from it at the rate of 360 kilojoules per minute. If the required power input to the refrigerator is 2 kilowatts, determine 1. The coefficient of performance of the refrigerator, and 2. The rate of heat rejection to the room that houses the refrigerator. So the coefficient of performance of the refrigerator is QL divided by W. We could also write this as .QL, the rate at which heat is removed from our refrigerated space, divided by .W, the rate at which work is supplied to the refrigerator. We've been given .QL as 360 kilojoules per minute. To convert this to kilowatts or kilojoules per second, we divide 360 by 60, which is the number of seconds in 1 minute. And doing this, we get .QL as 6 kilojoules per second, or 6 kilowatts. We've also been given the work input as 2 kilowatts. So the coefficient of performance of our refrigerator is equal to 3. For a refrigerator, QH minus QL equals W. So QH equals QL plus W. And .QH, the rate of heat rejection of the refrigerator, is equal to .QL plus .W. So we obtain .QH as 8 kilowatts. For the next problem, A heat pump is used to meet the heating requirements of a house and maintain it at 20 degrees Celsius. On a day when the outdoor air temperature drops to -2 degrees Celsius, the house is estimated to lose heat at a rate of 80,000 kilojoules per hour. If the heat pump under these conditions has a coefficient of performance of 2.5, determine 1. The power consumed by the heat pump, and 2. The rate at which heat is absorbed from the cold outdoor air. If the house loses 80,000 kilojoules of heat per hour, then to maintain its temperature, the heat pump has to supply 80,000 kilojoules per hour to the house. So the rate of heat supply, .QH, equals 80,000 kilojoules per hour. To convert this to kilowatts, we divide by 3,600, and we obtain 22.2 kilowatts. We've also been given the coefficient of performance of the heat pump as 2.5. And for a heat pump, the coefficient of performance equals QH divided by W, or .QH divided by .W. So 2.5 equals 22.2 divided by .W, and we obtain .W, the rate of work input to our heat pump, as 8.88 kilowatts. To calculate the rate at which heat is dissipated, .QL, we use .QH minus .QL equals .W. So .QL equals .QH minus .W. And we obtain .QL as 13.32 kilowatts. There are many valid statements of the second law of thermodynamics. In this course, we're going to discuss two: the Clausius statement and the Kelvin-Planck statement. The Clausius statement can be expressed as follows. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. The Clausius statement makes a lot of sense because we know that heat does not on its own flow from a colder body to a hotter one. This doesn't mean that we cannot construct a device which removes heat from a colder body and transfers it to one that is hotter. In fact, that is what refrigerators do. It simply means that for this to happen, work must also be supplied to such a device. The Kelvin-Planck statement can be expressed as follows. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. This tells us that no heat engine can convert all the heat it receives to useful work. The waste heat isn't due to dissipative factors or irreversibilities. Even under ideal conditions, there is still waste heat, and this is because for the cycle to be completed, heat must be rejected to a lower temperature reservoir. For example, let's take a look at this simple heat engine construction, consisting of a fluid contained within a vessel and fitted with a piston above it. This fluid is meant to accept heat from a high temperature source and convert this heat to work by expanding and raising a given amount of weight through a certain distance. And remember, for it to be a heat engine, it must operate in a cycle, so the fluid must return to its initial state once the work is done. The system is brought into contact with the high temperature source and heat is transferred to it, so the gas expands and there is also a temperature rise. In the process of expansion, the fluid is able to do work by lifting the weight. Apart from the energy required to do work, there's also energy required by the fluid to undergo expansion. The heat energy absorbed supplies energy for both, and according to energy conservation, the heat supplied is equal to the sum of the work done by the fluid plus the energy required for its expansion. So now that the work has been done, and we remove our high temperature source, in order to complete this cycle, the fluid has to return to its initial state. To do that, it must reject the extra expansion energy it received so that it can return to the state it was in before expansion. The only way it can do this is by rejecting this energy as heat. But it can't reject heat to the high temperature source, because heat doesn't flow from a body at lower temperature to one at a higher temperature. So for heat rejection to happen, we need a low temperature sink. We can now see that for us to have a cyclic device which converts heat to work, there must be heat rejection to a low temperature reservoir. The consequence of the Kelvin-Planck statement is that a heat engine cannot have a thermal efficiency of 100%. Either one of both statements, Clausius and Kelvin-Planck, can be used as the expression of the second law of thermodynamics. Both statements are equivalent in their consequences, and we can demonstrate this by showing that a violation of either one of these statements would violate the other. Consider the combination shown. We have a heat engine which violates the Kelvin-Planck statement in combination with a refrigerator. The heat engine absorbs a quantity of heat from a high temperature reservoir, and it converts all of this heat to work. And this serves as the work input to the refrigerator, which absorbs a quantity of heat QL from the low temperature reservoir. In conformity with the energy conservation principle, the refrigerator rejects an amount of heat to the high temperature reservoir, which is equal to the sum of the heat absorbed and the work input. The net amount of heat transferred to the high temperature reservoir is equal to QH plus QL minus QH, which gives us QL. Therefore, the net effect of this system is to absorb a quantity of heat QL from the low temperature reservoir and transfer it to the high temperature reservoir, which violates the Clausius statement. In a similar manner, we can show how a violation of the Clausius statement violates the Kelvin-Planck statement. Here, we have a combination of a refrigerator which violates the Clausius statement and a heat engine. The heat engine rejects the same amount of heat the refrigerator absorbs from the low temperature reservoir. The net heat rejected is equal to 0. And the net heat absorbed by this system from the high temperature reservoir is equal to QH minus QL. So what we have is a system which absorbs a quantity of heat QH minus QL from the high temperature reservoir and produces an equal amount of work in violation of the Kelvin-Planck statement.